when we apply reinforcement learning is to compute a policy, which is a mapping from states to actions. So for each state that we encounter in the environment, our policy will provide us the action, hopefully the optimal action with respect to our reward function, but also with respect to the future reward, the next states the action is going to lead us to. So the policy should optimize the expected value of the objective function or the sum of reward that we encounter while completing an episode through the MDP, through the Markov decision process. We learn from interactions with the environment. That is, each time we observe a state and choose an action in the environment, the environment changes and we reach a new state. We learn what is the benefit from performing a given action in a given state following these transitions. And we update the policy such that the expected benefit is maximized over time. This is known as online optimization. We optimize our policy while interacting with the environment and following these interactions. So next, we would like to evaluate. So as I said previously, we have various RL approaches, to perform reinforcement learning. And we would like to evaluate our algorithms on different metrics. So first of all, we would like our RL algorithms to converge on some policy. Mainly to avoid training divergence. So it might be the case that during training our policy diverges or the performance diverges over time. You see some examples of that. We would like to avoid this kind of divergence. We would like to avoid suboptimal convergence. So we would like to converge, to have our policy converge, but we would like it to converge on the optimal policy as much as possible, of course. That requires us to balance the exploration in our state and action space and exploitation of the known best action at the moment. Okay, so exploitation will be required in order for us to converge on a policy, but we would need to perform sufficient exploration in order to actually discover the optimal policy, to converge on the optimal performance. We would like our algorithms to be as efficient as possible, so we will measure that with respect to sample efficiency. That is, how many interactions, how many times we need to interact with the environment in order to discover and converge on the optimal solution. This can be measured either by number of interactions with the environment, the number of time steps required for us to converge, or in episodic settings such as playing an Atari game, a video game. This is often measured as episodes until convergence, how many games we had to play until we actually converged on the optimal solution. We will consider some other aspects such as safe exploration. How can we balance sufficient exploration but also provide some safety guarantees? We'll also try to avoid biased learning, that is converging on some suboptimal solution due to inherent bias in our reward function or in the environment. We will also discuss the notion of regret, that is during training, how, we'll define it better later on, but how suboptimal do we perform during learning? So in many, specifically in real world applications, we would like to perform well while learning to perform better over time. So finally, I would just like to mention that RL, we cannot say that RL is solved. That is, if you have a real world problem where RL reinforcement learning is applicable to, I can't promise you that it will work great just from the start. There are some many existing challenges that you should be aware of. There are some good solutions, I would say, or more recent work tries to address these issues, and it might require you to dig up some papers and look at the literature and Google some existing solutions. But hopefully, this course will give you a good basis to later on continue to do your own research and find relevant solutions to the specific problems that you're trying to solve later on. So I have a list here of a lot of the existing challenges in RL. For instance, training offline from fixed logs of an external behavior policy. So this can tie back to the example that I showed you before with the traffic signals. it would be great if we can pre-train some RL controller for the traffic signals just by looking at the existing suboptimal controllers out there, and then optimize based on that. But this has some issues with that. We'll might be able to discuss those later on, or we'll discuss some of these later on when we discuss transfer learning. And there are many other problems or many other challenges. I don't want to go into each of those, but these are available here. You can read on those. And these might be challenges that are relevant to a specific application that you are trying to address. So just be aware that I would say RL is not completely solved at the moment, right? And you might encounter some challenges, specifically in specific applications that you're trying to address. But know that the existing literature or the existing scientific community is actively working on addressing these issues, and you might need to look at some recent paper in order to find good solutions. And by the way, we will discuss some of these issues later on. I mean, we will encounter them also during the course, and I'm guessing you will encounter them during your project, the course project that you will address during this course.